Welcome back to ME 760 Engineering Analysis 1. So we are in the same business for solving the differential equation, ordinary differential equation using the power series method. Today's lecture will be the last lecture in this business in the power series method. And starting from next lecture, we'll start a new topic about linear operators until the end of the semester, which will be next week, hopefully next week. So we discussed the solution, power series solution, around a singular regular point, and we stated that there is three types of situations. Can you remind me what's the situations that we might find? R1 and R2 aren't the same.
And their difference is either an integer or not integer.
And difference, R1 and R2, they are not the same, but they differ by an integer. And the last one is R1 equal to R2. So we solved it for R1 and R2 are not the same, and we found a solution for this situation, yes? The only problem we found last time is when R1 equal to R2 or R1 minus R2 differs by an integer. We stated that we have only one solution and we have to find the other solution. So one of the methods for finding the other solution was the Wronskian method that we described last time. So before we start the new method, which is the derivative method, let's just review a little bit what we did for the last couple of lectures. So if we are giving the partial differential equation y double prime plus p y prime plus q y equal to 0, and we can write this in an operator form, that the operator L applied over the function y equal to 0. So we will call this 1, where the operator L is just equivalent to d2 by dx squared plus b of x d by dx plus q of x. So our general approach from the beginning was to substitute with a function y of x and r equal to x to the power of r summation from n equals 0 to infinity an, and we note that an is also a function of r. When we solve for the initial equation, then we got the recurrent relation. We note that an is a function of r multiplied by x to the power of n, and we will call this equation equation number 2. And I have to remind you that we picked up a naught where a naught does not equal to 0. So if we substitute in equation 1, we will find the values of r and the values of a sub n, and this is what we used to do for the last couple of lectures. So that the operator L of y of x and r is satisfied and it's equal to 0. So usually we substitute and collect terms, excuse me, and collect terms with equal powers of x to get a relation like the operator L applied over R, y of R and x is just equal to summation of some formula, and this is what we used to see all the times for the last couple of lectures of Pm xm plus R. So you remember when we substitute with y from 2, y equal to x to the power of R, summation of an x to the power of n, we substituted in the differential equation, we got to some certain expansion here or summation of some terms. We call this term Bm multiplied by x to the power of m plus R. And what are the Bm's? Those Bm's are functions. It's a function of am, a, m minus 1, and so on. And for 2, this expansion here for y to satisfy one, we used Bm, P sub m must equal to 0, and this is what we use to do for all m greater than or equal to 1, Bm equal to 0, and this will give the recurrence relation. Am has some form, mathematical form, multiplied by am minus 1, for example, and this is, we'll call it 3, and this is a recursion relation. So this is what we used to do for the last couple of lectures, that we try to solve the Frobenius method for solving the partial differential equations. And usually y L operated over y of x and R will be just B naught multiplied by x to the power of R, where B naught is just the coefficient of the lowest power of x, and we can say that this is equal to A naught multiplied by R minus R1 multiplied by R minus R2 multiplied by x to the power of R, and I will call this equation number 4. Again, you have to remember that A naught does not equal to 0. So just when you excuse me, when you take your notes, remember to put the 1, 2, 3, 4, and so on, because during this lecture I will refer a lot to substituting 4, substituting 3, and so on, so that you will know where we are heading to. Okay, guys? So now, the requirement that B naught equal to 0 gives R minus R1 multiplied by R minus R2 equal to 0, and this is what we stated last time as the indicial equation. So the steps is, we have a differential equation. You will look for the regular points and the singular points. You try to solve around the regular singular points. You will expand y in the form of x to the power of r, summation from 0 to infinity, an x to the power of n, and this is the Frobenius method. Substitute back into the differential equation, get the summation formula, solve for x equal to 0, get the indicial equation, then take this indicial equation, substitute into the collect the terms of x to the power of n, and then substitute with the value of r to get the solution from the recurrent relation. So thus, this is just a review of what we used to do. So thus far, 2 to be a solution of 1, we require that R equal to R1 or R equal to R2. Because if you look here, when you substitute in the differential equation with y as the expansion of an x to the power of n multiplied by x to the power of r, we will reach to b naught x to the power of r. Then the differential equation states that the operator L operated over y of x equal to 0. So for this to be equal to 0, r should be equal to r1 or r should be equal to r2. So this will give you the left-hand side equal to 0. So this is the requirement that we impose. So let's try to see. The first step is to seek a solution, a second solution when r equal to r1 equal to r2, and this is what we stated last time. So the first case, r1 equal to r2, and we will let a naught equal to 1 for simplicity. So if we assume that am where m greater than or equal to 1 are chosen according to equation 3, this is equation 3 here. We do not know what's the form of the function here for the recurrent relation. So if you return back to your last couple of lectures, there is lots of form that we obtained from solving different differential equations. So if we assume that it will be governed by this, then equation 4 will give us, when we pick up a naught equal to 0, so equation 4 will give L y of x and r equal to the following: a naught equal to 1, so this is the remaining. We will pick up r1 equal to r2, so this is r minus r1 multiplied by r minus r1, so this is r minus r1 squared multiplied by x to the power of r, so this will give us r minus r1 all squared multiplied by x to the power of r. So if we differentiate this equation, the previous equation with respect to r. If we differentiate this equation with respect to r, this will give us d by dr for L multiplied by y of x and r equal to d by dr multiplied by r minus r1 all square x to the power of r. So how to perform the differentiation? So this is, you just said I will differentiate this linear operator here, L, with respect to what? R. But what's L? It's differential operator with respect to what? X. So it does not matter if you change the order. If you first differentiate this with respect to R, then take the differentiation with respect to X, it is exactly the same. If you differentiate this with respect to X, then differentiate with respect to R. So it's exactly the same. So we can just start with the differentiation with respect to R for y, x, and R. And what's the differentiation of this? It is the first multiplied by the differentiation of the second. Differentiation of second is what? 2 multiplied by r minus r1. Yes? Multiplied by the first is x to the power of r, plus the second is r minus r1 square multiplied by the differentiation of the first. What's the differentiation of the first? Nope. Differentiation of the second is just x multiplied by ln r, because I am differentiation with respect to r, not with respect to x. Yes, if you have y equal to a to the power of x, and I told you differentiate this with respect to x, you will tell me that this is dy. Before you do this, you will take ln y equal to x ln a, and then differentiate this. This will give you 1 over y dy by dx equal to, differentiate this with respect to x. This is constant, so this will give you ln a. So dy by dx is just equal to y multiplied by ln a, and y is just a to the power of x multiplied by ln a. So it is exactly the same here. Okay, guys. So this will give us x to the power of r. Okay, x to the power of r multiplied by ln r multiplied by this one. So from this, we will see that the linear operator of d by dr y of x and r will equal 0 when r equal to r1. Yes? So when r equal to r1, this will be equal to what? 0. So what does it mean? It means that this is a solution for the differential equation. Yes? Because this is, substitute with something inside the differential equation, and it will satisfy the differential equation. It says that this is equal to 0, so this is also another solution. So thus, d by dr y of x and r evaluated at r equal to r1 is also a solution, and we will call this y2 of x. And this is star. So this is also a solution for our differential equation. But do you want to keep it like this, or do you want to simplify and figure out what's the solution will look like. Usually you want to simplify it and search for some analytical form, and instead of just saying y2 equal to d by dr for y of x and r. So in order to find the explicit form, what we will do, what's y1? y1 of x and r. y1 of x and r is x to the power of r what? r1 multiplied by what? Or x and r multiplied by an as a function of r multiplied by what? X to the power of what? To the power of n. So this is the y1. So to get y2 of x, you just differentiate y1 by the r evaluated at r equal to r1. So if we differentiate this, so it will be, which one has the r here? X has an r and a has an r. This does not have any r, so this is constant with respect to r. So it will be the first multiplied by the differentiation of the second multiplied by the second plus the second multiplied by the differentiation of the first. So this will give us what? d by dr for x of r summation an of r x to the power of n. And this is just, again, the first one. We'll take this as the first one multiplied by the differentiation of this. The differentiation of this, we just got that this is x to the power of r ln what? Ln r. And this is evaluated at what? All of this is evaluated at what? R equal to r1. So this will be r1, r1. Yes? Actually, this is ln x and not ln r. Yes, multiplied by an of r1 x to the n plus the second multiplied by x to the power of what? R multiplied by the differentiation of the second. The differentiation of the second is what? Dan of r by the what? By the r multiplied by x to the power of n. But we have to, after we did this, we have to evaluate this and substitute with what? R equal to r1, and we'll put here r equal to r1. Where do you think n will start from? Here is n start from 0 to infinity, and here we will start with n equal to 1. Why?
So you differentiate an, you'll lose your a naught term.
Exactly. When you differentiate this, you will expand it. Yes? So a naught is constant, is equal to what? 1. So you will lose a naught, and you will start from a1, a2, and a3. So this is why we have this one here. But what's this? What's, let's write, instead of this, let's change this to be x to the power of r1 ln x. What's this? Y what? y1 of x. So it is ln x y1 of x plus what? Plus x to the power of r1 summation of this term multiplied by x to the power of what? N. So we can remove this one and we name it bm or bn x to the power of n, where bn is just dAn by dr evaluated r equal to r1. And we can remove this one to be y1 of x plus x to the power of r summation from n equal 1 to infinity bn x to the power of n. So this is y2 of x. Okay, guys? So all what you do is what? If you want to find y2 is here. It's ln x multiplied by what? y1 plus x to the power of what? r multiplied by r1 multiplied by summation of bn x to the power of n. So you will solve excuse me, you will solve the differential equation, find the recurrence relation. Recurrence relation will have n and r in the recurrence relation, differentiate it with respect to r, and this will be what? bn, yes? Then raise x to the power of what? r1, then get the solution that you already got from the series solution as y1 multiplied by ln x, and this is the y2. This is if we have r1 equal to r2. What about if we have r1 minus r2 will be equal to, case number 2 will be equal to integer. So we have to look for this case as well. So the case for r1 minus r2 is equal to some integer. So we will multiply equation number 4 by r minus r2, so that the linear operator is here. Where is equation number 4? It's not in the blackboard. So this is r minus r2. Does not make any difference if you multiply r minus r2 here and you bring it inside the operator, because the operator is with respect to what? X. So this is a constant with respect to x. So I can bring it in. So r minus r2 multiplied by y of x and r is equal to a naught just 1. We will take it for the simplicity. R minus r1 multiplied by r minus r2 square now multiplied by x to the power of r, and we'll call this number 5. You will notice that r minus r2 multiplied by y of x and r is also a solution of 1 when r equal to r2. So when you substitute r equal to r2, this will give you what? 0. So operator L, this is the operator for the differential equation, operating over a new function equal to 0. So this function satisfies the operator equation. So it does satisfy the differential equation. So this is a solution. Yes? But do you think, is it linearly dependent or independent? Maybe we have a solution, but the two solutions are linearly dependent. So I cannot take it as a solution, linearly independent solution for the differential equation. It cannot constitute the second solution. So However, it can be shown that the limit when r goes to r2 for r minus r2 multiplied by y of x and r will be just some constant c multiplied by y of x and r1, which is just c multiplied by y1. What does it mean now? I will not give the proof here, but it can be shown that if you take the limit for r minus r2 multiplied by this function y of x and r, it will give you some constant multiplied by y of x and r1, which is c multiplied by y1. So what does it mean? It means that what we look here as a solution is just some constant multiplied by what? By y1. So it's not a linearly independent solution. The second solution cannot be taken as a linearly independent solution. So we have to seek for or look for another solution that's what? Linearly independent from the first one. And this will come the hard work. Excuse me. So we will again differentiate equation number 5 here. This is equation number 5. So this will give us d by dr with respect to r, of course. This will give us d by dr for L of r minus r2 multiplied by y of x and r and this will give d by dr r minus r1 multiplied by r minus r2 all square multiplied by x to the power of r. So the left hand side will be just r minus r2 all squared. When you multiply it by, you will take this, so the first multiplied by the differentiation of the second. So the second, the differentiation of r minus r1 is just 1. So 1 multiplied by this. Then the first r minus r1 multiplied by the differentiation of the second. The differentiation of the second is 2 term now. So it will be the differentiation of this while you fix this. So this is 2 multiplied by r minus r2 multiplied by x to the power of r plus again r minus r1 multiplied by this, which is r minus r2 all square multiplied by the differentiation of this one, and the differentiation of this one is just the same function x to the power of r ln x. Okay guys, did you understand? And this will equal to 0 when r equal to what? When r equal to r r2. R equal to r2, this term is 0. R equal to r2, this term is 0. R equal to r2, this term is 0. Okay guys? Thus, what do you think? What is the second solution? Thus, the second independent solution will be just coming from when you differentiate this here with respect to r. So y2 will be just d by dr of r minus r2 y of x and r and all of this evaluated at R equal to R2. So we can do the same to find the explicit form, and instead of just leave it like this. So we'll do the same and try to find the explicit form like here. So again, this is again what? Y1, I left Y1 over here. And Y2 of x is just d by dr of r minus r2 multiplied by what? X to the power of r, summation from n equal to 0 to infinity of an of r x to the power of n excuse me, and this is evaluated r equal to r2. When you do this, you will obtain ln x multiplied by r minus r2 x to the power of r, summation of an of r x to the power of n. This is evaluated at r2 plus x to the power of r2 summation of n equal to 0 to infinity d by dr of r minus r2 multiplied by an of r multiplied by x to the power of n, again evaluated at r2. So here we did not start with from what? 1 y, because we have now r minus r2 multiplied by an, even if a naught is a constant, but it will be multiplied by what? R minus r1, so the differentiation will not give you 0. Yes, guys? Last time we do not have this term. So when you will expand, you will have a naught plus a1 x1 x to the power of 1 plus blah blah blah. But for this one, we have r minus r2 term multiplied in front. So to simplify this one and give the general form, so y2 of x would be just equal to some constant multiplied by 1 of x, because this term here is what? Ln x, yes? And this is what? Y1, but when you substitute with r equal to what? R2, yes? So this will be what? R equal to R2. Or let me check, because there is a, no, it will not give 0. There is a, let me check what I did as a mistake. it will not give 0 because of the formula. I have to write the formula again, that the limit when r, you have to take the limits for when r goes to r2 for r minus r2 of y of x, and r, I just showed to you that this will give us c multiplied by y of x and r1, and this will give you c multiplied by y1. I just stated this 2 minutes ago, and this is 6. Label this as 6. So it will not give you 0 because you have to take the limits when r goes to r1. So this will give you c multiplied by y1 multiplied by ln x plus x to the power of r2 multiplied by summation of bn x to the n. Okay, guys? Maybe there is a time for an example to clarify this. Then we will stop. Again, you will find this method in the handout that I publish online for the second part of the book. Of course, all of you got the first part of the book. This book was previously, up to the last year, it was one single volume. Then starting this year, the author split it to 2 different books. And I ordered this is the first time I teach the class, so I ordered the first volume, and Dr. Schultz used to teach it for the last couple of years from the original 1 volume book. So this is why he taught those 2 chapters or 3 chapters from the original one. So when I order only the new version for the first book, and I did not know that you will need some chapters from the second one. So this is why I uploaded the other 2 chapters for you guys. And maybe there is another chapter that I will upload too for the last portion of the course. So y double prime plus 3 over x minus 1, y prime plus 1 over x minus 1 multiplied by y equal to 0. Definitely there is 2 points, x equal to 0 and x equal to what? 1. Those are the 2 points. So earlier during this work we found the recurrence or recursion relation for this equation. I'm not going to derive it again, but the recursion equation, and we found also that R1 is equal to 1 and R2 equal to 0, and the recursion relation was just an equal to n plus r divided by n plus r minus 1 multiplied by an minus 1. So we will do exactly the same. Like you will say, okay, first step, y equal to x to the power of r, summation from n equal to 0 to infinity, an x to the power of n, take it, substitute it here, then do what? Get the terms equal x equal to what? 0. You will get the equation, indicial equation. Solve the indicial equation. You will find that r1 equal to 1 and r2 equal to what? 0. Return back, collect the terms for x to the power of n, and this is the terms of x, the relation that govern the an and an minus 1 with respect to n and r. Then you will substitute with r equal to 1 to get y1, yes, and then r2 is equal to 0. We found out that when r2 equal to 0, this will equal to what? 0, and this will equal to what? 0. So n over n minus 1. What happened for a1? Nope. N1 explode. N1 is infinity. So we said, oh, we have two different roots, but they differ by an integer. So we find only one solution. The second solution is not there. It's not possible to find the second solution. Here it will come this method to play here. Okay, guys? So taking A0 equal to 1, we got A1 equal to what? R plus 1 over R. A2 equal to R plus 2 over R plus 1 multiplied by A1, which is equal to R plus 2 over R, and so on until you get AN equal to R plus N divided by R. Okay, guys? So y of x and r is just x to the power of r summation from an x to the power of n from n equal to 0 to infinity, and this is just summation of n plus r over r x to the power of r multiplied by x to the power of n. So we have one solution, which is this one. If you just run it over, you will obtain x over 1 minus x all square. And r equal to what, guys? For y1, so this will be x to the power of what? 1, and this will be x to the power of 1, and this will be what? N plus 1 x to the power of n multiplied by x. So this is for the first solution. Second solution, y2 of x will be just equal to d by dr, r minus r2 multiplied by y of x and r. So this will be equal to d by dr, r multiplied by x to the power of r. Yes? So this is r multiplied by x to the power of r multiplied by the summation of r plus n divided by r x to the power of n. R2 is 0, so r minus 0 is r multiplied by y of x and r evaluated at what? R equal to what? R2, which is equal to 0. Then when you do this, this will give you the following after you integrate, differentiate x to the power of r ln x summation from n equal to 0 to infinity n plus r x to the power of n plus x to the power of r summation from n equals 0 to infinity x to the power of n and evaluated at r equal to 0. When you evaluate it, this will give you x ln x, the summation of n, x to the power of n from n equals 0 to infinity plus the summation of x to the power of n from n equals 0 to infinity. The first term will give you x divided by 1 minus x all square multiplied by ln x So this is x, this is ln x, and this formula here will give you 1 minus x all square. And the second one will give you 1 over 1 minus x, which is this formula here. Then you can simplify it to x over 1 minus x squared multiplied by ln x plus 1 over x minus 1. So maybe if you have a Mathematica online, the Wolfram website, just log in the formula here and write ODE or whatever to get the solution. So pretty much you will get this. Okay, guys. So we will stop here and continue next time. Did you have any questions? Again, please, guys, for those who do not finish the online survey, the TVAL, it will take you just 2 minutes to finalize it. It's just quite few questions that has 1 to 5, so it will not take 1 or 2 minutes for you to finalize it. So it's very important for me so that I got this for the evaluation. So for the online students as well as for those students here in the class, please do diligence and just finalize it. I do not ask you to do anything other than just finishing the TVAL. That's it. So thank you so much. Have a good day.